8M6 Lesson 11, using linear models in a data context. Today what we're going to do is to review what we did in Lesson 10 really quickly with defining independent and dependent variables. We're going to go through a unique example using data to work on dependent and independent variables, and then draw a best fit line, calculate that line, and then answer some questions about that line. Then what I'm going to do is I'm going to do something that I typically don't do, but I'm going to show you a cool tool that you can use to find best fit lines that will give you the exact best fit line using advanced techniques that will be learned, you will learn how to do in high school. But instead of doing the technique, this will just give you that line directly. And maybe you can use this from time to time in class or on your homework to draw those lines. Because sometimes it's cool to see exactly what line best fits the points and look at the characteristics of those lines. Okay, so that tool is coming at the end. So let's get to it. We're going to talk a little bit about Lesson 10, go through one example, and then go look at that tool. Okay, so let's pop on over to our sketch pad, and let's just start off on just answering this quick question. This came out of today's lesson, and it's kind of a review of it is a review really of Lesson 10, and it asks which way should we be looking at this certain data. So you talk about this geyser. A geyser is a thing that shoots out of the ground with water. It's like a water spout, and it's really cool. I've been there, and you go and you're at Yellowstone Park in here in the United States. It's a national park, and you're looking at this little hole in the ground, and there's fences. You can't get any closer to this geyser than this fence will allow, because this water will come spurting out, and the water's really hot. And so every like 45 minutes or so, this water spout comes out of the ground, shooting out and spraying everywhere like a fountain. It's really cool. But sometimes the geyser erupts longer, and sometimes it erupts shorter as this water shoots out of the ground. And so they took this data, and they found that after 1.5 minutes, one time it shot 3,700 feet of 3,700 gallons of water. They measured all the water. Then it went for 2 minutes, and then it shot more water. After 3 minutes, it shot more, and after 4.5, it shot even more water. So the question is this a linear model? How do you model it? One, how to model, and I'll explain that in a second. Two, is it linear? And then three, what is the equation that models the data? So we're not going to answer question 3 here. That's something that you did in class. But really, the question is which way are you going to model this data? Are you going to put the length on the x and the amount of water on the y? Or are you going to put the length is going to be the y and the amount of water be the x? So in other words, are we going to stick with this is B below and this is A below? Right? A says we put the amount on the x and the length of time on the y, and B has a model where you put the length on the x and the amount of water on the y. And remember back to Lesson 10, what we're asking. We're saying, well, which one, the one that we want to put on the x-axis is the independent variable. This is the predictor. And another way that sometimes that you can think about it is it's the one that's easier to measure. That's kind of the one that I like to think about. What's the easier one to measure? So which is it? Are we going to model it where we say, well, let's calculate the amount of water that comes out of the ground, and then let's see if we can guess the length? Or are we going to measure the length of time that erupts and then make a prediction about the amount of water? Which one's going to be easier for you to measure? That is going to be probably You can pause it, and then I'll tell you the answer. So you can pause. Really, the one that's going to be easier to measure is the length, because all you need to do is use a stopwatch to time it. Here, if we want to get the amount of water that came out, it's going to be very hard. We're going to need like some giant, you know, I don't know, giant bucket, and somehow catch all the water. So that's one reason that we're gonna rule out A. We're gonna say that's not our good model, and B is our good model. But really, what's gonna happen usually? Usually, you are gonna simply be asking the question. You're gonna say, well, how long did it erupt for? Oh, it erupted for 4 minutes. Okay, well, in 4 minutes, how much water do we think you put out? If this is our line, it's going to be here. If it erupts for 3 minutes, about how much water do you think it'll put out? Well, that's going to be about here. 2.5 minutes, it's going to be about here. So I don't know if this was a great explanation, but we got to be looking when we're modeling data. There's usually one thing that's easier to measure. We're going to put that on X. It's going to be the first thing we measure, and then the thing that we're trying to predict what happens is usually on the Y. We're going to predict the amount of water based on length. Okay, I don't know if that was, again, great explanation. Well, let's move on to another example where we're going to try and guess which is the independent and dependent variable, but we're going to go further, and we're going to go ahead and build the linear regression, or the linear model. Okay, so here's my question. So here's two pieces of data, the same data that's presented in two different ways. So we have, and this is going to be homework help. This is homework help. So sample mass scores on an SAT for 20 students along with the time that they studied. So here's a student, for example, that studied 4 hours, and that student scored a 390. Now, if you know anything about the SAT, the minimum score is a 200, and the maximum score is an 800. It's kind of a weird scoring system, but the 200 is the min, and an 800 is the max. Okay, so let's see. So the question is there which is the dependent and which is the independent variable? In other words, which is the number that we're going to first look at and then try and guess what the second number or what the second variable is? We're going to build a model, and on that model, we're going to have a line that looks like this. We're going to have a best fit line. Now, are we going to use that line, and we're going to ask the question generally, for a given amount of hours studying, what is the math score? Or are we going to say, well, what is the math score, and then how much time was spent studying? What is the thing that's generally going to be the first thing that we can know? The first thing that we can do? What is the first thing that we kind of have control over when we're going to be taking this test? Do we have a control? Can we say, I'm going to get exactly this score and then see how much time studying? Or are we going to say, I have control, complete control over how much time spent studying, and then we're going to see what math score I can predict? That makes sense? So which one can I know in advance? Which thing, if I'm a student and I'm working hard, which number can I know for 100% sure that I can do? Can I know my score in advance, or can I know how much time I'm going to spend studying? Well, I think that you've probably figured out that you actually can control the time spent studying. So that's going to be our independent variable. So let's go ahead and let's reveal the answer. Oops. And there is our answer. Down here, we're going to put, indeed, that our hours studying is our X variable, which is our independent variable. It's the thing that we have control over. We have control over. Okay, so that means that it's not this one. So I'm going to delete that one. And I've already put the points up here. And so you can now try and draw your best fit line. No, it's not ours. This is our score, our SAT score. And we've done some techniques to find our best fit line. I'm going to go ahead and draw it for you, what I've found to be very good estimate, which is this one. Okay. So that's a pretty good fit line. And let's just look at this for a second. Well, we kind of have this outlier here. But other than the outlier, if we look here, we've kind of, maybe we've underestimated. Maybe we have, well, it's kind of an interesting, because you kind of count the outliers, these ones that are down here. And then if you look at these ones up here, a best fit line may be not quite so linear. It may be something more, a little bit like this. But we're going to use a linear regression for purposes of this example and purposes of calculating the best fit line. So at any rate, you may have had a line, I don't know, some of you may have had a line that looks more like, I don't know, more like this, maybe more like that. And that might be okay, as long as you can justify your reasoning on a test. We haven't learned yet how to find the best fit line, and so that's okay. As long as you can have a line and you can justify which one you use, your teacher should be quite okay with that. But this one is the best fit line. And how do I know? Because I'm going to tell you, I kind of cheated because I know the real answer, and I'll show you using this really cool tool here in a second how I know that this is in fact very close to the best fit line. Okay, so now that we have this best fit line, we've done one. We've figured out which one is the independent variable. We know we've drawn the line. Now we're going to calculate the equation for the best fit line. Okay. All right. So if you want to do that, I'm going to suggest that you pause and try on your own. And the key is going to be to find two key points that are right on, that are kind of far apart and are right on intersections of lines. I'm going to give you a hint. Here's a good one right here. It's got to be on the line, 2 points. You're looking for 2 points on the line that are easy to identify. So this one's easy to identify because it's at 14, 700. Right? This one's at 14 and at 700. Okay, so I assume you now have paused and tried. Now, the other point I'm going to use is far away, because further away usually gives you better numbers if the 2 points are far. If they're really close together, it's going to not give you quite as good a point, usually. Okay, so 0, if you knew the exact number, it would be fine. But if I make a little bit of error and my points are far, that error is going to be kind of corrected by the distance. All right, so this is 0, 350. Okay. And the other advantage of using this point at 0, 350 is that I now know this is my B, so I don't even have to calculate. I don't even have to calculate my B because I know it because it's right here. Now let's find our slope. So our M is equal to y2 minus y1 over x2 minus x1. And in this case, that's 700 minus 350 over 14 minus 0. So that's equal to 350 over 14. And that's actually equal to, let's see, 350 divided by 14. That's actually equal to 25. Let's see if we can figure out why that's true. So we have 175 over 7, right? If we divide by 2 and divide by 2. And 175 over 7 is in fact 25. Is that right? 175 divided by 7 is 2. 2 times 14, 35, 25. Wow, a nice even 25. So we know m is 50, so our best fit line using our kind of estimate here is y equals 25x plus 350. Who'd have thunk that would have worked out so nice? So that's good. Let's just happy cat this and take a little victory right now. Now let's answer this question. What is predicted for a student who studies 8 hours? So let's pretend we study 8 hours, and let's see what we think our score might be. Oops. So if we study 8 hours, that comes to right here, and then that would be what score? 4, 5, 6. Now that would be 500. So we think that the score would be a 550. Let's see. So using the graph, we think it's 550. Now using the equation, we would plug in 8 into our equation right here, and let's see what we get. Y equals 25 times 8 plus 350. Y equals 200 plus 350. Y equals 550. Good. And that should work out. So we predict a SAT score 50 if we study 8 hours. Now we can study more hours and we can get a higher score. And how much? What increase in score per hour? Now here's a good question. I didn't think of this until just now, but let's ask this question, and I'll ask it in green. What increase in score per hour studied should we expect? And I want to give you a hint. Think slope. What is the slope of this line? What are the units? Think slopes units. Think of the units of the slope. Okay, the units of the slope are SAT, the score per hour studied. That's the units of our slope. And our slope is what? 25. So we predict 25 score increase because it's positive. So we think we're going to increase our score 25 points per hour studied. And that's exactly right. Because let's put in the hours of 10. If we put in 10, we would expect 2 more hours studied. We'd expect a score of 600, right? We'd expect 600 because we'd expect 25 and 25, 50 points better if we studied an extra 2 hours, given our slope. And let's see if that's right. 10 times 25 is 250, plus 350 is 600. So we'd expect with 10 hours, we'd get a 600. And so that's exactly right. So what increase per score per hour? 25 points per hour. Now what I want to do is I want to show you, so let's happy cat that. I want to show you one last thing. I want to show you a tool that can give you this exact number. And let's go ahead and see if we actually got it right. Remember, 25x plus 350 is what we think this data should regress to if we had a perfect calculation. Now, what I'm going to show you is, let's go, it's called Desmos. So we're going to go to this tool called Desmos. I'm going to show you how to type it in and exactly what's going to happen. You go to desmos.com, and then you type in start graphing. Okay. Now, I'm going to kind of move this graph a little bit. And now what we're going to do is we're going to create a table of data. And so we do this thing called table. We do this plus thing and go table. And then we're going to just start typing in our data. We had 4 hours of study. You got a 390. And then if you studied 9 hours, you got a 580. And if you got a 10 hours, you got 650. And if you studied 14 hours, you got 730 and so forth. Now, if you want to graph this data, the graph, you notice that by default, you get these weird numbers, or you get these small numbers. So I want to make my x-axis be between, 0 and like 30. So I'm going to go over here to my graph settings, way over here on the right, and I'm going to say I want my x to be between, well, we'll do -5 because we want a little extra space, and 30, like this. We can even add a label and call this hours studied. We'll call that, go to 30. And now this will be my SAT score. And I'll say my low number is going to be like -100, which can't happen, but it'll give me some extra space. And then my high score will be 900. I want to go a little past 800. So there we go. And so now we have a nice graph where we can see some of these points. Now, rather than go ahead and have me enter all 20 points here, I'm going to go to a saved graph because I've saved all of this data on a different graph. So let's do that. Let's go there. And this is all of my data. And notice I've typed it in over here. Now, this still doesn't have your best fit line on it. So you've gone ahead and typed in all your data. Now I want to put in my best fit line. And the way that I do that is I'm going to create a formula, and it's going to give me that M and that B without having to calculate it. It's going to be using those advanced techniques that we've learned about, that you will learn about in high school. So what we do is we say, we're going to write a formula, and we're going to make it look like y equals mx plus b with a couple exceptions. Notice that this is called x1 here, and this is called y1. So we have to use those variable names, y1 and x1, instead of x and y. So I'm going to go to my calculator and say y1. And now the way I say best fit is I don't put an equal sign here. And this is a vagary, a nuance of Desmos. I'm going to put in this twiddle sign. Some people call it a tilde. And I call it's at the top left of my keyboard. And it's on, I have to hit Shift, and then I hit my tilde. So find that tilde sign on your keyboard and hit that in. And now we're going to say M, which is the thing I want to find. And I'm going to then say X1, because I want to find MX1 plus B. And so this is exactly what your formula should look like. And notice it drew you a pretty good best fit line. And so that's how you find your best fit line. You can use this tool, Desmos, to do that. Now look at what they think M should be. They think it should be 25.3, and we had 25x. So they say it's 25.3 is the real number. And then B should be not 350, but it should be 353. So that's how you can use Desmos to find any best fit line for any set of data that you have. And it's really cool because that happens really fast. And so interestingly enough, they have this thing called R squared. And this tells you how close it is to being a really good line. If this number is close to 1, then it's a good line. If it is not if it's not a good fit, this number will be less than a half, closer to 0. So this R squared can go anywhere from 0 up to 1. And again, closer to 1 means it's pretty much a line is a good way to model your data. Okay, so that is it for today's lesson. Hopefully it was useful. We basically gave you one example, the problem set. I think there's 3 examples in it, and you just are going to be doing the same thing over and over. You're going to be finding best fit lines. You're going to be modeling data, finding best fit lines, answering some questions about that data, and then we're moving on. So lesson 12 is next, and then we have 13, 14, and then you're done with the year. So give yourselves a hand. I'll give you a hand too. All right, we'll see you next time on Happy Cat Math.